to thank you for inviting me to Kyoto. This is my third time here. My apologies, I'm presenting in English, but it is a great honor to be here, and I also thank Kyoto University for this very stimulating forum. I want to share with you today two different sides of my job. I'm the director for astrovisualization in New York City at the American Museum of Natural History, the Hayden Planetarium, which is now part of something called the Rose Center for Earth and Space. On one side, I direct the movies that are created from data visualization at the new Hayden Planetarium we rebuilt 10 years ago. And on the other side of my job, I work with overseeing software development to try to visualize what we call the digital universe, a project to bring together a data atlas of the universe in 3 dimensions. And the results of that I want to show you now. This is, what you're looking at is the solar eclipse from July 22nd of 2009 this year. And you're seeing an image of the Earth on that day from the Terra satellite from NASA. That you're seeing a simulation of the eclipse, but you're seeing a real image of the Earth. I'll just point out, if I bring my cursor over, you can see that there's some strange artifacts that you see. This is because the satellite goes around the Earth every hour and a half, and the Earth turns underneath. And as the Earth turns, we get another scan. And so you can think of the Earth moving actually as one part of the scanning mechanism as the satellite goes around taking this image. And so I'm going to show you this interactively. This data of the Earth I pulled down last night, interactive online. This is available through NASA, through the Goddard Space Flight Center, brings the data down. And a friend of mine at NASA's Jet Propulsion Laboratory processes the data into a global map. You can go to a website, which I'd be happy to give you, to actually look at the details of this data. You can also see the global image flat on that website, on Earth, just like ONEARTH, on Earth.jpl.nasa.gov. Also, it's on another website called Flash Earth. So what we're seeing here is this interactive view of the globe in space, and this software, UniView, which Dr. Ebazazaki-san mentioned, and it's being used in the Sinra Dome. This was developed by my students. I've had 12 students from Linköping University in Sweden. And I just want to say that I met Dr. Ebazazaki 10 years ago, and I was very excited of the interactivity that the Universe Live show in Tokyo was doing. When we rebuilt the Hayden Planetarium, our goal was to try to display the universe of data, our understanding of the modern universe, both by what we observe and what we can simulate with astrophysics. And at my museum, just as we have research paleontologists who collect dinosaurs in the field, we have research astrophysicists who are doing simulation research at the highest levels. And so we pull that together into our shows. So I'm going to first show you this interactivity, and then I want to show a clip of which I'll need some audio, actually audio hookup in the second part if that's possible, just from our recent show, Journey to the Stars. We've made 4 shows in the 10 years that we've been open, and so I'll get to that a little later. Well, let me come in and actually show you. I'm going to run time for us. let's run time a little backwards here first. So there's the eclipse moving across the Earth. And what's interesting about this, if you have an interactive display, is that, and my Milky Way is a little bright there, but here I'll just run the eclipse. We can see the edge of the eclipse coming across India. And you can see that the path just happened to be across some fairly cloudy areas, but if you're in Bhutan, you've probably got a good view, and then coming across into China. I want to make sure that, let me just verify that this is the right day. This is not the right day. Excuse me, just a moment. I have many things set up here. Just let me make sure that, okay. That's the correct cloud configuration. My apologies. So let's just run that back again. And so the cloud cover of that day. I started off, what you were just looking at was actually yesterday's cloud cover. So my apologies. So here, if you can see sort of through the clouds, here's Korea. And actually you can see Japan underneath the clouds here. I'm using just the fact that we get, this is where the sun reflection would be, and it sort of highlights the islands of Japan. And so we can see the eclipse passing over Shanghai right here. So let's go farther out, and I'm just going to set my display to current time. I just jumped to current time, and we see the current pose of the Earth, and we see the lights of North America. We also see a line, that's the orbit of the space station. And I'm now going to bring up the clouds essentially from about 24 hours ago. And once again, this is data that is taken by two NASA satellites. Let me actually put the microphone down. Not sure this is difficult to fly and operate at the same time. I'll do my best. There was a beautiful low pressure system out over the Indian Ocean yesterday. And so we can see it here in detail. And so, oops, just, okay, there. Oh, okay. Just a moment. There, I can move frictionless. Thank you. Thank you very much. Is that okay? Good. Thank you very much. As we come in over Thailand. And the part of the goal here is, and we project this in our dome at the Hayden Planetarium when we do a live presentation. We only do a live presentation once a month. If you come to my planetarium, you'll see a show that we create, and I'll show that in the second half. But right now, we've been developing this, and this has been a work in progress. This has been a development effort. But the goal, as far as my feeling is that we want to, in modern day, with the amount of data that's available, is to be able to put it into a context, put it into proper context, and see it on the globe. Another thing you see here is the atmosphere, its proper thickness, only 30 kilometers high before it starts going into black visibly. Of course, the atmosphere extends above that. 3 times this height, we're up to the base of the ionosphere,
the curtains of the aurora borealis. But this ability to sort of see what the astronauts would see. Once again, we saw the space station in the beginning. So I'll just, I see it coming around. So to give us a sense of what the astronauts would see from their perspective, let me just join up with the space station. And fly to it. The space station only flies 400 kilometers off the surface of the Earth, what we call low Earth orbit. And as we get close to it, we're going to see the same space station you saw in Ebisazaki-san's talk. This is from Toshiyuki Takahei, his model of the International Space Station. And it was a first effort of sharing together. He shared us this model, and also Toshi Takahei now works with the development effort on UniView. So this is essentially what the astronauts would see, their perspective on the Earth, how far away from the Earth. And what I'd like to do is just advance us over data that I was able to download. If I was live and online, we would be able to see, it would be paging in. But this is the perspective that the astronauts essentially have. Great. So how big is the universe? I'm going to just jump back to our view of the Earth. And start from here and move out away from it. And I'm going to do a simple, quick tour of the universe for you. There goes the moon. I should stop by the moon. I should stop by Mars and all the planets. But in order to do this quickly, I wanted to sort of give us a sense of the immensity of the universe. We live on this small planet. And if we can see it up close in all its beauty with the latest information, the latest data, and the latest pictures, and put that together into this larger picture of the universe, that's our goal. And to actually be able to show it like you could see it perhaps in a voyage of the imagination, we're already violating the speed of light. When I come into even this realm, it takes light a second and a half to go from the Earth to the moon after light has traveled 8.5 minutes from the sun. So let's move out. We see now the orbits of the planets. And so we see Mercury, Venus, Earth, Mars, and then Jupiter, Saturn, Uranus, Neptune, and we are showing the minor planet now, Pluto. And that when we get out here, we're sort of confronting a much larger scale. The solar system itself, we've been able to chart just within the last 30 years with Voyager going out past Neptune, and the New Horizons spacecraft now is on its way toward Pluto. But we begin to see this other line of the Milky Way. And so what I'm going to do is just rotate our view so the Milky Way will be sort of our new point of reference. And as we are about to pull away, I just point out that it takes light about 4 hours to go from the sun to Neptune. The nearest star, however, is this star, Alpha Centauri. And if we come out farther, we're going to now show the sun in its brilliance as we would see it as just another star. We had to artificially dim the sun in order to see it and up close in the solar system. So now let's pull back. And as we do, we can see Alpha Centauri start to move and the other stars start to move. So effectively what we've done is we've gone from the Earth. The Earth disappeared into the glare of the sun. Now the sun is disappearing into the surrounding stars, brought to us by distances from the European Space Agency's Hipparcos mission. The nearest star cluster to us is the Hyades star cluster, better known as the face of Taurus the Bull. These stars right in here, about 150 light years away. Having a little trouble navigating, having to look up and back at the same time. Let's pull back, and now we see just our local neighborhood of stars. We've only charted about 100,000 of these stars locally to us, a very small part of the Milky Way. This Milky Way model is from the 42U team, and we're also putting in an image of NGC 1232, a galaxy which astronomers consider fairly similar to our own Milky Way galaxy. So this being our Milky Way galaxy, we're about halfway out in a system of several 100 billion stars. It takes us 250 million years to make one orbit, and we've been around 20 times since the sun formed. The dinosaurs were formed when we were just one turn back. So let's pull back even farther, and we just passed our nearest large galaxy, Andromeda, and also the Pinwheel galaxy, M33. And we're seeing galaxies color-coded. This is color coding from the scientist Brent Tully, who looks for structure. These are 30,000 galaxies that surround us, so that we see them around us. We see in red the largest clusters, or the densest clusters. So we see here the Virgo cluster of galaxies. So we can see the universe is not evenly distributed. We're seeing the large-scale structure from these observations. Again, 30,000 galaxies sort of nearest to us, and we're the dot in the center. Every one of these dots is another galaxy. Every one of these galaxies, several 100 billion stars. So beyond this, we have deeper surveys. We see the Sloan survey coming up now. There's a survey of 700,000 galaxies. The color-coded galaxies, once again, are from Brent Tully's catalog. The outlier colored points are actually, each one of those points is a galaxy cluster from the Abell catalog. Now in yellow, we see a complementary survey to the Sloan, which is called the 2-degree field survey. We're now out so far at about this point where the galaxies start giving away to other objects, right here, where the galaxies sort of give way now to these much farther objects. The farthest objects are the quasars, but around this point, our distance, it would take light about 5 billion years to get to where we are. Now you ask, why is the universe sort of shaped like this? This effect of what we see over here is that this is where we have not looked yet. We have not actually pointed our instruments. And part of that reason is the Milky Way blocks our view, blocks a clear view of what we can see here. So we have not yet mapped here. Farther away, we see the quasars against now a background of the cosmic microwave background, which was discovered in 1964, was mapped most recently with the WMAP satellite. And I'll just pause here. This is, we get into some controversy in showing this image, but this shows the extent of our view. We can't see any farther back because this is the afterglow of the Big Bang. We're seeing so far away that light has taken essentially the age of the universe since the universe cooled from being a plasma several 100,000 years after the Big Bang. So this is our view of the universe, limited as it is. Larger than what we can see, but this is our local view of the universe. I'm now going to cruise back through 25 orders of magnitude, back through a grouping of data all put together to give us one consistent experience of the universe. Seeing the context and being able to see it seamlessly going from one point to the next allows us in this age of what media can bring us the ability to share this and see it. So what I'd like to do right now is just quickly transition. I'm going to try to switch my console back. And if you bear with me just a moment. The Hayden Planetarium, when we opened in 1935, had this optical, mechanical, traditional star equipment. This is the original Hayden Planetarium with some visitors. Venerable old planetarium was rebuilt. You can actually see the same building over here in the next photo of what's been rebuilt. So that's our starship. American Museum of Natural History, famous for its dioramas, dinosaurs, recreation of nature from around the world. These are cheetahs in their glass display. Academic immersive media, I just want to mention this planetarium tradition. But with technology now, we have the ability for full dome video and to make movies and interactives, but also network presentations and present science potentially around the world. The practices that I'd like to just emphasize here is the accuracy that we're showing you the real map, and our need to orient the viewer in this sort of abstract world, a world that we're unfamiliar with, and the context of the elements visually, so that we're seeing, again, just complementing on what building on what I just showed you, which is understanding these various parts by going from that which we understand, us, at the Earth, and moving out. And then depth cueing using motion, camera motion, to give us that sense and orientation of where we are. And so we've endeavored with the UniView software to make it networkable for multiple users around the world. And so we're using this feature called Octopus to domecast a network for simultaneous viewing around the world. So multi-user sessions to examine the universe in 3D. And the idea of having networking is that we can bring the facilitator, the scientist, lecturer, in from wherever they may be in the world. And so we have a growing number of these going on. I've taken 2 computers to Makara High School in Siem Reap in Cambodia, and we've been working with them. Here are the students working on the laptop that I took and left with them. And this is their teacher, Pirak, actually controlling the Hayden Planetarium from Cambodia. Ghana, this is one of the first digital planetariums in sub-Saharan Africa, and this was built by a retired professor's pension money, and Dr. Jacob Ashang. We see Dr. Ashang over on the right, and Dave Weinrich, who's actually the president of the International Planetarium Society, actually got this projector donated, and I presented from the Hayden Planetarium to Ghana for their opening. Medellin, Colombia, better known as a site of drug wars just 10 years ago, is underneath a tremendous revitalization, and they built a science center in a former poorest neighborhood of the entire city. And I went there just recently, and we basically did a simulcast from the science center to 5 libraries. The flagship of the new mayor is putting these in the poorest sections of town, and this is the Biblioteca España which was the first one built, and so we beamed that out to the kids. And also I was invited to come down to participate in a White House star party for the International Year of Astronomy on October 7th. And so we were actually linked up at the time to 3 planetariums in Minnesota. And Barack Obama and Michelle came out and viewed the universe that we were able to show in an inflatable dome out on the south lawn of the White House. And I just want to say a word for this networking ability is something that, to some degree, I was influenced by. I had a dialogue with Arthur C. Clarke years ago over artwork that I'd done on Mars, and I brought him the digital universe. And so from that, I was inspired to really try to bring that out to the world. What I'd like to do now is just run the video clip. I understand my time is up, but I just want to give you a sense from this. If I could put the audio plug in, that would be great. Thank you. There we go. Thank you. Great. This is from our current production The narrator is Whoopi Goldberg. And let me display you. Fit to screen. There we go. And you full screen. Let me just start it. Oops. The story of the sun that we go through here. I'll point out that
there's no better way to understand how a star works than to look at one up close.
Bringing together 40 scientists worldwide.
And there's
to really
no
make this
better
production.
star to examine than our very own sun. The star that nurtures and supports life on Earth.
Stereo spacecraft and SOHO.
3 satellites orbiting the sun not far from Earth took these images.
You can see the slight
They show the
perspective
sun's
shift based
outermost
on where the
atmosphere
spacecraft is
called the
looking at the
corona.
Milky Way.
Its outer layers escape in a continuous solar wind.
Moon's orbit, satellites.
See those trails in orbit around the Earth?
Geosynchronous
They show the
raying.
paths of satellites. Some of them watch the sun. Others observe the weather or broadcast TV and GPS signals.
November 7th, 2007, those are the images you're seeing from the heliospheric imaging satellite being replayed.
These solar close-ups reveal a star that is more than just a big ball of gas.
Ultraviolet image
These
along
glowing
with the
loops are solar storms.
chronosphere, or with the
Beneath them, darker, cooler areas form, called sunspots. The sun
Images from
generates the
SOHO.
energy we feel when we step out of the shade on a sunny day. But how is this energy produced?
it's a model from
Let's
Yuri
take a look.
Tumray and colleagues, University of Colorado.
This flow, just below the sun's surface, is similar to the churning of water just before it boils. Go deeper, and we can see the swirling currents of gas that carry the sun's energy outward.
A quantity called entropy. Squaring the vorticity gives you a scalar field that we can
This
visualize.
energy is generated deep in the center of the sun by one of the most powerful processes in the universe. Here, hydrogen atoms
Illustration.
smash together, forming helium and releasing huge amounts of energy. This is called fusion, and it's why a star shines. The balance between the outward push of gas heated by fusion and the inward pull of gravity is what makes a star a star. But the sun, like many stars, makes more than light. The churning flow also generates vast magnetic fields shown by these swirling lines.
Again, the model from Yuri Tumray and Ben
Sunspots form when magnetic field lines get bunched together. Some sunspots are larger than Earth.
Brown. Simulation from Matthias Rempel, High Altitude Observatory, Boulder, Colorado.
The dynamic wind that blows away from the sun drags the magnetic field along with it at 1,000,000 miles an hour. You heard me, 1,000,000 miles an hour.
Whoopi adding her touch.
Magnetic explosions on the sun can both drive strong blasts of this solar wind and produce dangerous radiation.
Solar magnetosphere, Thomas Gambosi and colleagues.
Blasts from solar wind
University
can
of
interrupt
Michigan.
TV signals and even cause blackouts. Fortunately, Earth's own magnetic field almost always protects us. Only a trickle of wind typically gets through, sliding down to the North and South poles. This causes radiant displays of light called auroras.
We wanted to illustrate how the solar magnetic field really exists throughout the entire solar system. 3 models.
We often think of space as empty, but the sun's influence reaches all the way out here and beyond.
How many minutes?
Just past this. We got to go out to 1 minute.
That's Saturn, another planet that has a magnetic field. Saturn has its own auroras. That line extending from Earth represents the path of Voyager 1, launched in 1977. In 2004, it discovered where the solar wind ends. Those are the greetings in 55 languages carried by Voyager on its journey to the stars. Just in case anyone's out there.
Hello from the children of planet Earth.
Voyager continues to travel across the region where the solar wind slams into the surrounding interstellar gas and the Milky Way's own magnetic field. The sun's power extends even beyond the solar system. But the sun won't always shine. What happens to most stars at the ends of their lives?
Thank you.
Okay, thank you very much for excellent presentations.
Thank you.
Yeah, I enjoyed very much. So, we spent time a little more. So.